of sort of an intermediate form between the two types of hybrid orbitals, or the two types of orbitals, and they're going to form hybrid orbitals around that central atom. So if we take a tetrahedral example, we'll use methane, so that's CH4. So if I draw that out, that's going to look something like this. And just as a reminder, those solid wedges mean it's coming out of the page, and those dashed wedges mean it's going into the page. So you have to visualize this as a 3D structure, okay? All right, so what happens is, in this CH4 molecule, carbon has to bond with those 4 hydrogens, which means there's 4 things attached to that central atom. So notice how, if we look at the periodic table for carbon, carbon is going to be in the 2s and the 2p block for its valence electrons, right? So its valence electrons are going to be in 2s and 2p. Okay. So what's going to happen is you have your s orbitals, which are shaped like spheres, and you have your p orbitals, which are shaped like dumbbells. And what happens here is you're going to produce 4, right? Because we have 4 things bonded to the central atom, so we get 4 hybridized bonding orbitals. And what happens is we get a hybrid shape in between these 2 shapes. So what that ends up looking is something like this. So part of it looks like that dumbbell, and part of it is more of a sphere on the top, okay? And you're going to get 4 of those. And so these are my sp3 hybridized orbitals, and there's 4 of them. So that's an sp3, that's an sp3, that's an sp3, and that's an sp3. Okay, so now what happens is, with the example of CH4, I have my carbon, and what happens is I'm going to get those orbitals, those hybrid orbitals that are pointing away from the carbon. And so let's use green to represent the bigger part of that hybrid orbital, and let's use red to represent the small part. So what happens is you have these hybrid orbitals that are facing off in the direction of bonding. Okay. So all those little small parts, they're all converging on that carbon, and all of the bigger parts are extending outwards, and they're ready to bond. Okay, so that's what that carbon is going to look like when it's hybridized. And so now what's going to happen is it's going to bond with the 1s orbitals of the hydrogens. So whatever the valence orbital of the outer electrons is, that does not hybridize, that just bonds with the hybridized orbital. Okay, so if we represent just the s orbital as that blue, so what's going to happen is with hydrogen, if we look at hydrogen on the periodic table, all it has is a 1s orbital, okay? And so we know covalent bonding is an overlap of orbitals, a sharing of electrons. So what's going to happen is each of those sp3 hybridized orbitals are going to bond with the 1s orbitals of the hydrogen. Okay, so each of those are 1s. Okay, so you have, in summary, the 4 sp3 hybridized orbitals bonding with the 1s orbital of the hydrogen. And that's what CH4 actually is in terms of its electrons, okay? So let's see, is there anything more? So let's talk about when we're bonding with p orbitals. All right, so I showed in this example, we're bonding with those 1s orbitals. You can also have those as p orbitals if that certain molecule calls for it. So basically the way you know to call for it is you take the highest valence orbital of that outer electron. So for hydrogen, it only gets that 1s orbital. But if we're using an example of, say, BF3, so the general structure for that is going to look like this. Remember, boron only wants 6 electrons in its valence, or in its octet, quote octet, it only wants 6. So it's only going to bond with 3 things, and there's not going to be a lone pair. So first of all, what is the hybridization of BF3 going to be? Or what's the hybridization of B going to be, boron?
Is it sp2?
Yep, good. So you figured that out because there's 3 fluorines bonded to that boron. There's no lone pairs whatsoever. So we get sp2 hybridization. Okay. So what's going to happen is we do the same thing where we create these hybrid orbitals, except in this case right here, it's sp3, meaning there's 1 s, and that's hybridizing with 3 p orbitals, okay? So 1 s, and it's going to hybridize with 3 of those p orbitals. So what you can imagine is that when you only have 1 of those 1s orbitals that's hybridizing with each of those 3 p orbitals, the 1s character doesn't get very retained. So it's just a very small blurb on top of those larger dumbbell shapes in the sp3s. But when we take sp2, then I get a 1s orbital, and that's hybridizing with only 2 p orbitals this time. Okay, so those hybrid orbitals have a bit larger s character on top of them. So that, you know, that little blurb on there is going to be bigger. Okay, so each of those are an sp2 hybridized orbital. Oops. So the way that's going to look is you have your larger s character of that sp hybrid or sp2 hybridized orbital, and then that's going to stick out. Like so. And so now let me get rid of these fluorines for a minute. So when I bond with the fluorines, am I going to be putting 1s or 2s orbitals right there? If not, what am I going to put there? Because hydrogen's highest orbital is a 1s, so what's fluorine's highest orbital? Exactly. Yeah, p. Yep. So what happens is this time we're going to bond head on with 2 p orbitals. And those are going to be the fluorines. So what that looks like is, it's going to look like this. Let me scoot that over. Okay, so those are going to be the fluorine 2p orbitals that bond with the sp2 hybridized orbitals on the central atom. So what you need to know for those exterior atoms, whatever the outermost orbital is, that's what's going to bond with the hybridized orbitals of the central atom. So basically, in summary, the central atom gets hybridized. So central atom hybridized orbitals bond with valence orbitals of the outer atoms. Okay. So a question here. So I drew those two p orbitals like so, but what if I were to draw it like that? So can someone tell me if that's correct or not and why? Not quite. Not quite. We'll get into those, but that's not exactly what I'm looking for. You're on the right track though. Okay, so basically the reason why that wouldn't work is because when we're bonding valence orbitals, they have to be head-on, okay? So it has to be head-on, end-to-end overlap of those valence orbitals. Okay, that's the only way that's going to work. So that may be a test question or a conceptual question, so you just need to know that it's end-to-end head-on bonding. So now, does anyone have any questions over valence bond theory and hybridization? Generally, the highest yield stuff is just going to be this rule, but just in case, I wanted to teach some of the conceptual stuff behind it. And if you're confused about the conceptual stuff, it makes a whole lot more sense once you take OChem. If you take OChem. Okay, so it doesn't look like anyone has any questions. So let's go ahead and move on. All right, so now let's talk about pi and sigma bonds, okay? So pi bonds, just the pi symbol, and sigma bonds look like that, okay? So pi bonds and sigma bonds, all right. So let's talk about the example of CH3, okay? So that molecule is going to look like this. Oops. Okay, so first of all, can someone tell me what the hybridization is on each of those carbons? Yep, exactly, because each of those carbons is bonded to 4 other things. So those are sp3 hybridized. Just wanted to test everyone there. Okay, so basically what's going to happen in that CH3 example is you have one single bond in between the 2 carbons and in between the carbon and the hydrogens. And when you have one single bond, that is going to be a sigma bond, okay? So each of those are sigma bonds. Okay. So basically, when you have one single bond, you get one sigma bond, okay? All right, so now let's use the example of CH2. okay? So first of all, each of those carbons is going to be sp2 hybridized because each carbon is bonded to 3 atoms. And then what we also need to know is in this Lewis structure, we actually get a double bond, okay? We get a double bond in between the 2 carbons, okay? So that's when we start to talk about pi bonds. So if we're talking about this from a valence bond orbital perspective, it's going to look something like this. So you have each of those sp2 sp2 hybridized orbitals. That looks something like this. And then you have the 2s orbitals of hydrogen bonded to the ends. And then you also have, sp2 overlap in between the carbons. And so that's going to also be head-on bonding. So head-on. So just to label this, that is an sp2, that's an sp2, 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 and sp2. And then each of those hydrogens are 1s. Okay. So what happens is we know that carbon is going to have an extra p orbital. So each of those carbons are going to have these extra p orbitals that are going to sort of look like this. They go above and below the plane because it's shaped like a dumbbell. Okay. So what's going to happen when we have those extra p orbitals, those are actually going to overlap, and that's going to form that pi bond. Okay, and that happens above and below the plane. So that whole thing that I have drawn in orange for you, that is one single pi bond. Okay, so in this case, when we have a double bond, so when we have a double bond, that is going to have one sigma bond, and it's also going to have one pi bond. Okay. So now let's use one last example, and I'm going to draw it down over here since we're going to skip this part. So now let's use CHCH. Okay. So we know based off the Lewis structure, we're going to form a triple bond in between those 2 carbons, okay? So basically each carbon is bonded to 2 other things, so each one is going to be sp hybridized. So what I have is an sp hybridized orbital bonded to one of the hydrogens and bonded to the adjacent carbon. Notice how I'm drawing the overlap in all of these diagrams to represent the bonding. Okay, and then I have the 1s orbitals bonded to the end on the hydrogens. But now, in this case, there's going to be 2 p orbitals on each carbon that's empty. So one is going to be above and below the plane like so. And then this is going to be a little bit difficult to draw, but one is going to be perpendicular to the plane. Okay, And so for each of those sets of 2p orbitals, they're going to overlap like so. So they overlap above and below, or forwards and backwards with the pink example. And so each overlap of 2p orbitals is one pi bond. So how many pi bonds are in this example? Exactly. So when you have a triple bond, you get one sigma bond, and that sigma bond is right here that I'm circling in green. That's our sigma bond, that hasn't changed. And then we have two pi bonds, okay? So the general rule that you need to know is when you have a single bond, that's just going to be one sigma bond. When you have a double bond, you're going to have your one sigma bond, and then you're also going to get an extra pi bond. And then when you have a triple bond, you have one sigma bond, and then two of those are going to be pi bonds also. So that's the general rule behind pi and sigma bonds. So does anyone have any questions over any of this before we move on? Okay, so let's go ahead and move on. So let's talk about IMFs. Okay. So there's basically, let's see, 1, 2, 3, 4, 5, 6 different types of IMFs that you need to know. But generally, the ones that are tested most commonly, there's only 3 of them. So I'll talk about that first. So of those first 3, the weakest one you want to know about is dispersion forces, and sometimes they're called London dispersion forces. Okay, so let's talk about what causes an intermolecular force. If you remember back to chapter 4, I believe, when we were talking about aqueous reactions, dissolving things, solubility, all of that, we were drawing some of those molecular diagrams to show how certain ions dissolved in water. So one of those looks like this. So let's say we're dissolving NaCl in water. So this is my water molecule. The red is oxygen and the gray is hydrogen. So I'll just draw 2 just for simplicity. So each of these are going to have regions on them, right? So now that we've learned about electronegativity, this makes this a bit easier to understand. So we know that the net dipole for these water molecules is going to look like this, okay? Because oxygen is the most electronegative, so it's going to have a partial negative on the side of oxygen, and those hydrogens are going to be partial positives. Okay, so if we're dissolving NaCl, then the Na is going to be attracted to the partial negative side. So that's my Na. And then the Cl is going to be attracted to the partial positive side, because I have Cl minus and opposite signs attract. So that minus is attracted to the partial positive side. With Na plus, that positive Na plus is going to be attracted to the partial negative side of the oxygen. So that was just that little refresher there. And you also know about how we figured out this dipole moment from the last exam, okay? So now, what do London dispersion forces mean? We talked about how some molecules are going to be polar and some molecules are going to be nonpolar, okay? So generally speaking, nonpolar molecules are not going to experience these types of attractions, right? Because there's no region of partial negative or partial positive, right? But in real life, of course, nothing is perfect. So those electrons are all constantly moving around. And since they're constantly moving around, there's a slight chance that at some given moment, they could be at some position that maybe produces some very slight dipole moment. And so that's the idea behind London dispersion forces, okay? So basically, the slight probability that a nonpolar molecule exhibits some form of polarity, temporary polarity. Okay, so this is going to end up being the weakest IMF. So weakest type of IMF. And also all molecules will have this. Okay, so all molecules, whether they're polar or nonpolar, will exhibit London dispersion forces, right? Because even with our polar molecules, they have a net dipole moment, but you know, those dipole moments can be changed just a bit depending on the exact instant where those electrons are when they're moving about the molecule. So that's, you know, the logic behind London dispersion forces, okay? And so just know those are the absolute weakest type of intermolecular force, okay? And so now we want to talk about which molecules are going to have higher IMFs and which ones are going to have lower IMFs, okay? So when you have a higher molar mass, so higher molar mass, then the London dispersion forces are going to increase. So I'll abbreviate LDF. So the impact of those London dispersion forces increase just because if we compare just a small molecule here, I'm not going to draw anything super specific, and a big molecule here, then those electrons moving about the molecule, in the large molecule, there's a bigger chance for, there's a bigger chance for those electrons to all polarize in some direction versus there's less electrons for that chance to happen in a small molecule. So generally, large molecules are going to have marginally larger London dispersion forces. So basically, if you're comparing two nonpolar molecules that only have London dispersion forces, then the larger molecule is going to have larger intermolecular forces between itself than the smaller molecule. Okay. All right. So next up, let's talk about dipole-dipole forces. Okay. So dipole-dipole forces are the next strongest of the three most important that you need to know. So let's go back to our H2O example, or let's do a general example without hydrogen, because hydrogen bonding is more specific. So let me just draw a generic molecule here. So let's say it looks something like this. And we have some lone pairs right here. So this could be NF3. In fact, yeah, let's do that, NF3. Okay, So what's going to happen is there's going to be a net dipole moment that's generally in this direction of NF3, because those fluorines all on the bottom, they're all more electronegative than that nitrogen will be. So those fluorines are all going to have partial negatives. And the nitrogen, by comparison, has partial positives, okay? So what happens is when you have multiple of these molecules in, a mixture or what have you, then what's going to happen is, just like how in dissolution, right, where the positively charged cation is going to be attracted to the partial negative side, and the negatively charged anion is going to be attracted to the partially positive side. When we have dipole-dipole forces, what happens is, if we look at this partial positive nitrogen, that is going to be attracted to those partial negative fluorines in a mixture, okay? So the molecule is going to orient itself like this in a, oops, it's not letting me. One sec. Okay, I don't know. Just imagine me rotating it. Perfect, okay. So those nitrogens are all going to orient and be attracted to those fluorines, like so. Okay. And so this one, those fluorines are all going to be attracted to the nitrogens like that. Okay, so that's what dipole-dipole force means. So the partial positive on one molecule is going to be attracted to the partial negative on another molecule. So partial positive on one molecule is attracted to the partial negative on another molecule. Okay, and so generally they probably won't make you do this on an exam. Like in London dispersion forces, we can use the molar mass to determine which molecule is going to have a higher London dispersion force. But with dipole-dipole, we have to know actually what the extent of this dipole moment actually is. So generally that's kind of difficult to do on an exam, but just in case, the more intense the dipole moment is, the more intense the dipole-dipole attractions will be. Okay. So the last one I want to talk about is hydrogen bonding. So I'm going to go ahead and erase this part here, and we'll talk about it. So number 3 is hydrogen bonding. So this one is the strongest type of intermolecular force that I would know if I were you guys. So of these 3, hydrogen bonding is the strongest. So let's talk about what hydrogen bonding actually means, okay? So first of all, hydrogen bonding has a very similar design or method as dipole-dipole. So first I'll write similar to dipole-dipole. Okay, and additionally, there's a condition to hydrogen bonding and whether or not it can actually happen. So what has to happen is there has to have a hydrogen bonded to either fluorine, oxygen, or nitrogen. So I just remember the acronym phone, right? So a hydrogen has to be bonded to a phone, and that phone is either fluorine, oxygen, or nitrogen. So if we take the example of H2O, so I'll just go ahead and copy this. So what happens here with this H2O, that hydrogen is going to be bonded to the oxygen on that molecule. So we know that we can get hydrogen bonding from this, okay? So next up, what happens is the electronegative atom that hydrogen is going to be bonded to is going to be attracted to the hydrogen on an adjacent molecule. So it looks like this, right? So the attraction is going to be from the electronegative phone to a hydrogen on an adjacent molecule that is also bonded to a phone, okay? If there is not a hydrogen bonded to one of these elements, you cannot have hydrogen bonding whatsoever. It's not possible. So another example where this could happen is NH3. So this example here was NF3, so that would only be dipole-dipole, but if we had NH3, then this molecule would be able to have hydrogen bonding. So there will be an attraction between one of those hydrogens and the electronegative atom that hydrogen is also bonded to on an adjacent atom, okay? So that's hydrogen bonding. So now just to basically list off the other ones that aren't as important, just in case, you have ion dipole. So ion dipole, that's basically solubility, right? That's this whole example here that I drew, that's ion dipole. So you have those Na plus ions attracted to the dipole partial negative on oxygen, and you have the anion attracted to the partial positive, so that is ion dipole attractions. And so of all of the intermolecular forces, this is the single strongest. But of the three that you'll see most often in this class and in other classes, hydrogen bonding is the strongest. Like in OChem, it's only these three that we talk about, okay? So we have ion dipole. The next one we have is called ion-induced dipole. Okay, and so with ion-induced dipole, basically what happens is we have some kind of nonpolar molecule here. So this molecule is nonpolar. And what happens is we put an ion next to it. So let's just pretend this is some very negative anion. What's going to happen is, since these electrons are all negatively charged and we're putting a negatively charged anion next to it, it's going to repel those electrons somewhat. Oops. So it's going to repel those electrons to the other side of the molecule, and it's going to scrunch them all up on this side. And so that forms somewhat of a induced dipole in an otherwise nonpolar molecule. And so now what happens is you get a partial negative on this side, a partial positive on this side, and all of a sudden there's an attraction between the partial positive region and the anion, okay? And the same thing can happen with a cation. It just does the opposite, right? So if we had a cation right here, then all of those electrons would flood towards the side of the cation, and it would just form a dipole that's the opposite direction, okay? And the last one you need to know is dipole-induced dipole. And so that's very similar to ion-induced dipole, but this time we're just pairing a polar molecule that's going to cause a non-polar molecule to become somewhat polarized in the same way, okay? And if anyone needs an explanation over any of these, then I can explain that at the end, because we'll probably have time. So is anyone confused over any of these intermolecular forces right now? Okay, so let's go ahead and move on into some practice problems. So I'll keep this page up so you can look at it and go ahead and work on number 1 and go ahead and type done or stuck in the chat box. And don't feel rushed because we have plenty of time to get through these. So just go ahead and work at it at a normal pace. All right, so is everyone still working, or yeah, my COVID test isn't back, so I'm freaking out. I'm literally just waiting to leave. Like the second that thing comes back, I'm literally speeding back home to Dallas. But like, is everyone still working, or? Okay. Okay, yeah. Just remember to explain or just say whether you're done or stuck, just so I know when you guys are ready for the answer. All right. So let's talk about this. So number 1 says, for the following, list all the types of IMFs that each molecule can have and rank them from lowest boiling point to highest boiling point. Okay. So first off, let's do C3H8. Okay. So that's going to look something like this. 1, 2, 3, 4, 5, 6, 7, 8. So that is the Lewis structure for C3H8, okay? So for a lot of those organic molecules, it's really easy to just do it pretty quickly. All right, so that's my Lewis structure. So now we need to figure out what kind of IMFs this molecule is going to have. So first off, as with every molecule, it's going to have London dispersion forces. So definitely going to have that. As far as dipole-dipole forces, this molecule is actually non-polar, right? Because if we talk about, comparing the CH bonds and how those vectors all sum up, those vectors are all going to point inward like this. And so what happens is these cancel out with these. So those are all canceled. And then these cancel out. So those cancel as well. So that results in a non-polar molecule. So I'll write non-polar. So there's no dipole-dipole. And also there's no hydrogen bonding. Because for hydrogen bonding to happen, hydrogen has to be bonded to a phone. So that's fluorine, oxygen, or nitrogen. And in this case, the hydrogens are only bonded to carbons, so there's no hydrogen bonding. So the only type of intermolecular force we have in C3H8 is London dispersion forces. So now let's move on to CO2. So that is going to look like this. All right, so first off, every molecule has London dispersion forces. However, as far as dipole-dipole forces, again, those vectors are going to end up canceling out. So this is a nonpolar molecule. So it's not going to have dipole-dipole, and there's no hydrogens, so it's not going to have hydrogen bonding either. So both of those only have London dispersion forces. So next up, let's do C2H5OH. So this molecule looks like this. Okay, so I have 5 hydrogens bonded to those carbons, plus I have my OH group sticking off to the side. So that's C2H5OH. All right, so as with every molecule, it does have London dispersion forces. And then also let's look and see whether or not this is polar. So those vectors are going to look like this. So this molecule is going to end up being polar. So those vectors end up canceling out. However, these two vectors here are going to add together, and they're going to be greater than the opposite, OH vector right there. So that's going to end up in the whole molecule having some form of polarity. So this one is going to be polar. So that means this one is going to have dipole-dipole forces. And so generally the vector is going to look something like this. So on this end of the molecule, we have a partial positive end, and this end is going to be partial negative. And then also we have a hydrogen that is bonded to a phone, right? Fluorine, oxygen, or nitrogen. So that means we also have hydrogen bonding as well. So H bonding. Okay. So now for CH3F. So that's what that molecule looks like. So first off, it does have London dispersion forces. And so now let's examine the polarity. So those vectors are going to cancel out that I just drew, so I'm going to get rid of them. However, these two vectors, oops, that's a messy arrow. These two vectors right here, those are going to add up to form a sum vector. So that's going to form a dipole moment. And it looks like that. And I have a region of partial positivity right here, and on the fluorine, partial negativity. So we do have dipole-dipole forces. Okay. However, we don't have hydrogen bonding because these hydrogens here, they're all bonded to that carbon, and they have to be bonded to a phone. So no hydrogen bonding. So what this question is list all the types of IMFs. So we've done that. And now we have to rank these molecules from lowest boiling point to highest boiling point. So we have to figure out how we're going to interpret boiling point as it relates to intermolecular forces. So for lower boiling point, those are going to have weak IMFs. So those are weak. And when we have high boiling point, that's going to be strong. Okay, because when we have very weak intermolecular forces, molecules that aren't very attracted to each other, it doesn't take as much heat to cause those molecules to boil off into vapor, right? So it doesn't take as much energy to overcome those intermolecular forces, versus when we have strong IMFs, then that boiling point is going to have to be higher. We're going to have to put in more energy to overcome those intermolecular forces. So we're ranking these from lowest boiling point to highest. So we're ranking these from weakest to strongest. Okay, so what we know is London dispersion forces are going to be the weakest, and then dipole, and then hydrogen bonding. Okay, so first let's look at the molecules where they only have London dispersion forces. Okay, and so that is going to be C3H8 and CO2. Okay, now because C3H8 has a larger molar mass than, actually, let's double check that, because looking at it, it could, let's see, 12 times 3, and okay, so that has a molar mass of 44, and then CO2. Okay, so these, they're going to have about the same, so we'll say they're about equal. Okay, so they both have a molar mass of 44. So the way this is going to work, starting out, we have C3H8 is going to be around equal to CO2, okay? But those two are going to be less than my C3HF, because C3HF, its most strongest intermolecular force is dipole. So next up is CH3F. And then finally C2H5OH. So generally, we want to pick just the strongest representative intermolecular force that's going to dictate how strong the overall intermolecular force is for each molecule. So if we're taking C2H5OH, for example, we're generally going to consider that hydrogen bonding as contributing most to the intermolecular forces of that molecule, for example. Okay. So does anyone have any questions over how I did anything for number 1? So someone's saying, wouldn't the CH bonds be stronger because hydrogen is smaller? Okay, so you're thinking about lattice energy. So that's that periodic trend where when we have the smaller atoms, the bond is going to be stronger. However, that only applies when we're talking about lattice energy. And when we're talking about lattice energy, those are ionic compounds, okay? So ionic compounds are the ones that form lattices versus our covalent compounds, which all of these are covalent. Those are going to form these 3D molecules. Does that sort of make sense? Okay. It's a good question, actually. All right, so if there's no more questions over that, then go ahead and work on number 2. And remember to type either done or stuck in the chat box, just something to let me know that you guys are ready to see the answer. So let's see. So we got 1, 2, 3, 4, 5, 6, 7, 8. 7, 8-ish of you guys are done. So once a few more people respond done or stuck, then I'll go through the answer. I'll go ahead and go through the answer now. So number 2 says, what is the strongest IMF of the following compounds? And identify the compound with the highest vapor pressure, okay? So let's do CH3Cl. So this looks very similar to CH3F, except we just changed that F to a Cl. However, it has the same type of intermolecular forces. So first it has London dispersion forces, and it's also going to have dipole-dipole. Okay, and that dipole moment's going to look something like that. So now let's do CH3CH3. So that one is going to look like this. Okay, so this one, first it's going to have London dispersion. And as far as it being polar, if we look at all of these vectors here, they all end up canceling out. So these vectors that I have crossed in blue, those are going to cancel out, and the last 2 vectors are also going to cancel out. So that's nonpolar. So there's no dipole-dipole attractions. And additionally, there's no hydrogen bonding because those hydrogens are only bonded to a carbon and they have to be bonded to a phone, okay? So London dispersion is the highest force that CH3 has. So I'll go ahead and underline the most important in each one. So now if we do NH3, we'll do that in black. So that looks like this. So first off, it is going to have London dispersion forces. Now let's see if it's polar. So you have to think about this in terms of its geometry. So let's redraw it with some wedges and lines. So that's going to look like this. So each of those vectors are going to look like this. They're all pointing upwards at that nitrogen in the shape of sort of a pyramid. And so they all end up summing up to form a vector that looks like this. So it is going to have dipole-dipole forces. Okay. And finally, those hydrogens are bonded to a phone, so it's bonded to the nitrogen, so it does have hydrogen bonding as well. Okay. So hydrogen bonding is the strongest of the 3 for NH3. So just to recap, CH3Cl has dipole-dipole. CH3 has London dispersion, and NH3 has hydrogen bonding. So now we need to figure out which one of these is going to have the highest vapor pressure. So vapor pressure obviously is the pressure that happens when you have a sealed container with a liquid at the bottom and it's vaporizing. And when it's vaporizing in that sealed rigid container, those gas molecules are being produced and it's causing the pressure in there to increase. So that's vapor pressure. So that was from the second exam. So basically what happens is when you have more gas being produced, more gas evaporating off, then that means the vapor pressure is increasing. So generally we would say that the higher vapor pressure is going to be formed by the most volatile compound, the most readily evaporating compound. And so if we're talking about readily evaporating, that means you don't need to put as much energy into it. So more readily evaporating, less energy you have to put in, which means the weaker intermolecular force is going to have the highest vapor pressure. So I'll write higher vapor pressure means lower intermolecular forces. Okay, so weak intermolecular forces mean it's going to evaporate easier, and as a result, it's going to evaporate more at the same temperature. So it's going to have a higher vapor pressure. So just to rank these to give you an idea, NH3 is going to have the lowest vapor pressure. So I'm just going to write that down here. So NH3 has the lowest vapor pressure because it has the highest intermolecular attraction. It has hydrogen bonding. So it takes a lot of energy to cause that to vaporize. So it's not going to vaporize as much. So NH3 has the lowest vapor pressure. Next up, CH3Cl. So CH3Cl, that's going to be intermediate. That its highest force is dipole-dipole. And then the highest vapor pressure is going to be CH3 because it has the weakest intermolecular forces. All it has is London dispersion. So it's very easy for that CH3 to go ahead and evaporate off. And since it's evaporating more often, it's going to have a higher vapor pressure. Okay. So does anyone have any questions over number 2? Yeah, so you can think of it as an inverse. Yep. So there's an inverse relationship there. Some of these problems you have to conceptualize what's going on, basically. So like you have to know, okay, my weak intermolecular forces, they're going to evaporate very easily, so that's going to cause the vapor pressure to increase. Okay, are there any more questions over 2 before we move on? Okay, so next up, let's do number 3. So go ahead and type done or stuck in the chat box when you're finished. Basically, you're just identifying the hybridization of each of the central atoms in each molecule that I've drawn from problems 1 and 2. So you can draw them below here if you want to do that again, or you can just label each central atom for their hybridization. let me go ahead and go through these answers now. All right. So I'm just going to go through for each of these molecules that we've drawn. So starting with my C3H8, we actually have 3 central atoms in this molecule, right? So each of those carbons. So for that leftmost carbon, I'll do these labels in green. So that leftmost carbon is going to be sp3 hybridized because it's bonded to 3 things. Same thing with the middle one, and same thing with the rightmost one. So all of those carbons are sp3 hybridized, okay? So now if we take CO2 as an example, that carbon is bonded to 2 other oxygens and no lone pairs, so that carbon is going to be sp hybridized. Remember, the oxygens, those are only exterior atoms, so they're not hybridized. Okay, so next up, let's do C2H5OH. So my central atoms here are these 2 carbons and also that oxygen as well, okay? So first off, for that leftmost carbon, that's going to be sp3 hybridized because there's 3 things attached to it. Same thing for the other carbon. Now for the oxygen, this one you want to be careful with because it's actually also sp3 hybridized because there's actually 2 lone pairs on that oxygen. And so that means there's 4 things bonded to that oxygen, so it's sp3 hybridized as well. Okay, so moving on to CH3F, there's only 1 central atom and it's the carbon, and so that one's going to be sp3 hybridized. So that's the hybridization for number 1, and then for the molecules in number 2, starting with CH3Cl, that carbon is also sp3 hybridized. And then for CH3CH3, both of those are sp3. And NH3, that nitrogen, is also sp3. So most of the molecules we talk about are generally going to have sp3 hybridization. It's just more common, at least in chemistry classes. I wouldn't say in the natural world. Okay, so that's basically the end of this packet and the end of this session. We actually finished right on time. So yeah. I didn't get my test results back, so I don't have to leave now. So if you guys have questions, then you guys can ask me those. So I actually do have time to answer questions now. Okay, sure. So first page is in this one right here. Miles, I did not hear what the average was. Hopefully it was higher. Okay, all right, so Laura's asking, why isn't NH3 sp2? So there is 3 atoms bonded to that nitrogen, so by that logic, it would be sp2. However, there's also that lone pair, and we count that lone pair as a group bonded to the central atom. So all of the atoms bonded to the central atom plus any lone pairs, there's 4 in the case of NH3, so that's why it's sp3. Yeah, I'll go to the next page. Oh, 79 class average? That's very high. That's good. Okay, and then there's that last page of practice. Okay, so someone asked, where was it? Someone wants me to go over the last 3 intermolecular forces. So do you mean the last 3 that I did from number 2, or like these last 3 right here? Okay, perfect, sure. So the first one there is going to be ion dipole. So ion dipole. And so of all of the types of intermolecular forces, this is the single strongest. So of the three I emphasize and of the three most common you'll see in chemistry, hydrogen bonding is the strongest, but outside of that, 3-ion dipole is actually the strongest, okay? So let's talk about what's actually happening. So first off, just the word ion dipole, that means we have an attraction between an ion and some kind of polar molecule, right? So ion with a polar molecule. Okay. So let's do water, for example. So water is going to be our polar molecule, and then I'll have an ion paired with it. So that red, actually, I'm just going to draw the structure because I'm used to drawing the diagram, but now that we've learned about Lewis structures, let's do the structure. Okay. So this is my Lewis structure for H2O. So let's say we are pairing it with an Na+, right? So we're dissolving NaCl in water, so that causes those Na+ ions to be floating around the water. And they're going to be very attracted to these water molecules because of the fact that due to the polarity of water, I get a strong partial negative on the side of oxygen, and I get partial positives on the side of hydrogen, okay? And because there's a partial negative on that oxygen, that Na+ is going to be very attracted to that the partial negative region of oxygen because opposite charges are going to attract each other. So the cation is going to be attracted to the partial negative region. So what you need to know is generally, if we're talking about cations, so cations will be attracted to the partial negative of the polar molecule. And secondly, if we're talking about anions, those are going to be attracted to the partial positive. So if I had my Cl minus right there, that's going to be very attracted to the partial positive hydrogens on both ends because the Cl is a minus and opposites attract. Okay, so that is ion dipole. So next up, what was the next one? It was ion induced dipole. Okay, so ion induced dipole. Okay, so this time we're pairing an ion with a nonpolar molecule. Okay, so let's pair an Na+ with, let's see, which one of these was nonpolar? Let's do CO2. That's not. All right. Okay, so the reason why I don't like to teach this as much is because this gets a little bit confusing and it's very low yield. But because you want to know, what you're going to have to think about is you're going to have to think back to resonance, okay? So if you think about how resonance worked, it was those electrons were moving around the molecule, right? And in real life, those electrons can delocalize and move around. They're not in like this rigid Lewis structure where there has to be, 4 lone pairs on that oxygen, right? In reality, it's just their regions of electron density and their regions of low electron density, and that can change as those electrons move around, right? So it's not a perfectly static picture. So what happens is when we take this very positively charged cation and we stick it on one end of one end of a nonpolar molecule, what's going to happen is the electron density is going to move close to that Na plus molecule because the electrons are attracted to that positive charge in the sodium. So what's going to happen is if I were to draw an electrostatic potential map of this, red symbolizes very high electron density and blue symbolizes very low electron density. So what's going to happen is in this normally nonpolar molecule, what's going to happen is those electrons are going to pool around that oxygen because it's close to that positively charged cation. So it's going to form this induced dipole, okay? So we get this temporary induced dipole where there is low electron density on one end and high electron density on the other, which causes there to be a temporary dipole. So now that there's this temporary dipole, all of a sudden there's a partial negative end and a partial positive end, and that's further attracted to that positive cation, right? That positive cation is attracted to that partial negative there, okay? So that's ion-induced dipole. So next up we have dipole-induced dipole. Okay, so this one is going to be a polar molecule paired with a nonpolar molecule. Okay, so let's pair HF with CO2. We'll do that. So I have my HF like so. Obviously, the dipole moment is going to look like this, right? So we have a partial positive on hydrogen and a partial negative on fluorine. And so let's put it next to a CO2 molecule. Oh, and one thing I want to note, just going back to ion-induced dipole, the second we take this Na away and we remove that outside influence, all those electrons are going to shift back to their normal positions, okay? So it's not like this permanently produces a dipole there. Okay, so back to dipole-induced dipole. This time, right, our force that's causing this normally nonpolar molecule to become polar, we're just making it a very polar molecule this time. And so this polar molecule has a very strong partial negative on the fluorine. So what's going to happen is all of these electrons in this CO2 molecule, they're going to want to move away from that partial negative, right? Because like charges are going to repel. So those electrons are all going to pool on the other side of that molecule. They're going to get as far away from that partial negative as they can. Okay. So the red, once again, symbolizes very high electron density. The blue symbolizes very low electron density. So what happens here is we have our high electron density and our partial negative, and we have our low electron density and our partial positive. And so we have a partial positive on the molecule attracted to the partial negative on the dipole molecule, okay? So that is all of those. So basically, the reason why these last three aren't as emphasized as much is because we're all talking about two different molecules attracting towards each other in these, versus in the three that I showed you, generally it's going to be the same molecules, right? So like if we're talking about ion dipole, obviously you can't have a molecule that's an ion and a dipole and it's the same thing. So with ion dipole, it has to be two different things. Same thing with ion induced dipole, two different things attracted to each other. And finally, with dipole induced dipole, two different things attracted to each other. Versus with these three that I showed you here, these can be referred to the forces between identical molecules. You can have London dispersion forces between two different molecules. You can have dipole-dipole forces in between two different polar molecules. And you can have hydrogen bonding in between two different molecules as well. But these are the only forces that we can use to characterize forces in between the same molecules. So that's why these are much more common when we're talking about intermolecular forces. Okay. So yeah, that's pretty much a deep dive into those last three. Okay, so someone says, what was the answer to the last one? I assume you're talking about number 3. So basically it's just all of these, green writing, that's where I symbolize the hybridization for each of those central atoms. Okay. So does anyone have any last questions before I end the call? All right. So if there's no more questions, then I'll go ahead and end the call. This is the only session this week. Every SI leader only has one session this week. So Creighton only has one and McHalen will only have one. So don't accidentally log in at Tuesday because I won't have one. So I hope you guys have a great Thanksgiving, and the next time I'll see you is when we're prepping for the final. So until then, goodbye.